going to share the book. So there I'm sharing. So yesterday we are looking at forms of carbon, giant atomic structure or giant covalent structure. And we are looking at diamond. And the second type of element that you're going to look is a special type of carbon called graphite. Graphite, we say, is also a form of carbon, but the atoms are arranged differently, although it still has a giant structure. Now, remember in diamond, if I can take you there up, the arrangement of carbon is in a tetrahedral structure. They are forming a 3D structure. In the case where each atom is attracted to one atom, and this structure continue on and on and on. But for graphite, which is also a form of carbon, has the atom arranged differently as that of diamond. But we say they are still a giant structure. For graphite, instead of existing as a tetrahedra, so they exist as a rare structure. They have a rare structure, rather like a pack of playing cards. As you can see in the picture there, you can see a pack of.
Is it this one of a line? It's like lines.
Yeah.
Is it that one?
So yeah, like this one. Now, the reason this arranged this way is due to the arrangement structure or arrangement of atom in a graphite structure. So in a pack of cards, each card is strongly, but the individual cards are easily separated. One card is very strong, but the individual card is easily separated. So you can see from here, you can see from this picture, you have atoms in layers of graphite. You can see you have the first layer. Let me highlight that one. Have the first layer. This is the first layer. Then you have the second layer,
graphite,
and so on. They exist in layers. Now, this explains the reason why graphite is used for fabricating, because it layers right over each other. So it's very good for fabricating, given that it has higher melting and boiling point.
Sir, hold on.
Yes?
Sir, even a graphite is used in playing cards.
No, they're just explaining like the way the layer of cards are arranged. That's how the layer of graphite are arranged. The way you can see cards arranged. You can see each card is very strong, but between one card and the other, there is a space there. So it can slide on top of the other. It can slide on top of the other. And that sliding explain the reason why graphite is used as a lubricant. The fact that it has a higher boiling and melting point due to strong carbon-carbon bond, it is easily used to fabricate machines that have higher intensity of temperature, because it can't melt easily. So you can say graphite is also used at the red pencil. You can see that pencil that you use, that's what you use there is graphite. It's graphite. That's why it's able to slide on a book and leave marks. It's able to write with your pencils. Although the forces holding the atom together is in each layer are very strong. The forces holding atom together in each layer. So atom to atom, carbon bond to carbon bond in each layer is very strong. It's very strong, but the attraction between layers are much weaker, and that's why there is no bonding between these layers. That's why they are much weaker, and there's not much energy which is needed to overcome them. And this explains why these layers slide over each and the other and can easily be fracked off. So you can say, and that's why I explain why the graphite is used as to manufacture of pencil, because you can see graphite, which is mixed with clay to make it harder. It mixed with clay to make it harder. So without clay, it's not harder. It's used to make it.
What mix with it?
Yes.
What does it mix with something to make it harder?
So you mix with clay soil. This is the clay soil.
Oh, clay.
Soil. Yeah. So we mix with clay to make a pencil to make it harder, and that's why you use it to making a pencil. Now, when you write, you leave a pencil.
Okay.
With a pencil, you are leaving a tray of graphite layer behind on the paper. Like we light, then that lighting is layers of graphite. You are sliding each layer and you're separating those layers. Pure graphite is slippery, that is used as dry lubricant. For example, powdered graphite is used to lubricating locks. Dry graphite to lubricating lock. So graphite also has a high melting and boiling points. And to melt or to boil a graphite, you don't just have to separate the layer. You have to break up the whole structure, including the covalent bond. And these covalent bonds are very strong. They are giant attraction. They are carbon bonds, which are very strong, that need very large amount of energy because the covalent bonds are very strong. Very strong. And we say graphite conducts electricity. Why does graphite conduct electricity? And hence it doesn't have free ions or free electrons. Why? Because if this can slide on top of each other, if they can slide on top of each other, therefore that layer, as it moves from one point to the other at this side, they can transfer electricity. And that's why they are good conductor of electricity. Now let's look at this figure. Figure 8.31, the previous page, this one, figure 8.31, the one which you have layers. So you have first layer, second layer, and between the layers you have weaker process of attraction between this layer. But attraction between carbon and carbon is a covalent bond. If you can look at that, you will see that each carbon atom is joined by only 3 others. Yes, it's joined to 3 others. But what do you expect? You expect the carbon to be joined to 4 other carbons for it to have noble gas electron structure. But in this case, it's just joined to 3 others. So each carbon atom uses 3 of its outer shell electron to form 3 single covalent bonds. The 4th electron in the outer shell of each atom is free. It's free. That's another reason why it conducts. Free, it have free electron, and also it slides on top of each other. So you can look, we have other properties of graphite. Other properties of graphite, you can say graphite is insoluble in all solvents because it would take too much energy to break all strong covalent bond. And this too much energy that can be required or will be required to break this bonding, make it or explain why this graphite is insoluble in all solvents. May it be organic solvent like methyl benzene or porous solvent like water. So all solvent, graphite is insoluble. So again, graphite is less dense than diamond. It's less dense than diamond because the layers in graphite are relatively far apart. If these layers are relatively far apart, the distance between the graphite layer is more than twice that distance between atoms in each layer. So you can now try to relate. The distance is twice as large as that distance between atoms in each layer. In sense, a graphite crystal contains a lot of wasted space, which isn't there in diamond crystal. And this wasted space explains why diamond is less, or graphite is less dense than diamond because of this wasted space between graphite layers. But we said graphite is a carbon, diamond is a carbon. Now we want I want to introduce you to another term, allotrope or isotope. Diamond and graphite are 2 allotropes of carbon. Allotropes, they are different forms of a same element. These are the same element of carbon, but this same element exists in different forms and exists in different forms. And if an element exists in a different form, we say it has allotropes. It has allotrope or isotopes. So another allotrope of carbon, we have carbon 60. Carbon 60 carbons in an element of fullerene. Fullerene is another allotrope of carbon, having 60 carbon in its structure, fullerene. And we have diamond and graphite are other allotropes that has 80 carbon atom, 80 carbon atom. We can have another different point between these three allotropes is fluorine has a simple molecular structure. Fluorine exists as a molecule, has a simple molecular structure. So it is a simple molecular structure. It can exist as a liquid. It has a low boiling point, it has a lower melting point as compared to graphite and carbon. But don't forget, it's the same element, but this same element exists in a different form. It's like a chameleon. It can like form this form, or you can find it in another form. So a different form. So in solid or liquid, C60, which is fluorine, there are C80 molecules with weak intermolecular forces between them. The fact that C60 has a simple molecular structure has a big influence on the physical properties. The physical properties because of simple molecular structure. So in this physical property, let's look at the physical properties of fluorine. They have lower melting and boiling point than diamond and graphite. And we say that fluorine is melted only, and I repeat again, only the relatively weak intermolecular forces of attraction must be broken. Those forces of the intermolecular forces of attraction is the only thing you need to break. It does not require as much energy as breaking strong covalent bond with diamond and graphite as melting. So you can see as this structure is the structure, the simple molecular structure of fluorine. So they exist in 660. Between them, you can see this form. This is one 60 carbon atom. This is another 60 carbon atom. So it's a molecule. It's a molecule. But between them, there's two structures. We have intermolecular forces. Between the other, we have intermolecular forces, and so on. And see in the faint gray color, joining all the molecule, which is weaker intermolecular forces of attraction. So still on combined bond. So fluorine is not as hard as diamond. It does not take as much energy to break the intermolecular forces of attraction. And also fluorine does not conduct electricity. Although all the carbon atom is in C60 or in fluorine only form 3 bond. You can see the form 3 bond. The fourth electron on each atom can only move around within the molecule. It can use, yes, three carbon or 3 carbon attracted to 1 carbon. So, and this carbon requires 4 electrons to be stable. And since the fourth electron it's mobile, it can move. It can only move between the molecule. It cannot jump from molecule to molecule. And if it cannot jump from molecule to molecule, it explains why this fluorine C60 carbon with 60 carbon atom in itself. So it does not conduct electricity. So that is covalent bonding. Covalent bonding, if you can recall all of that, we said there are two. We have a simple molecular structure and a giant atomic, the giant structure. Yes, giant covalent structure. For simple molecular structure, we have a photon, and most of them exist as a fluid. But for giant, they exist as solid. Giant, they're very strong. They are giant. So you can add there that topic. Not adding the lesson, but adding that topic. There's some question there, chapter question. I want to give you one on page 96. You can do number 1 and number 2. Number 1 and number 2. The next thing from there is page 96. Page 96, number 1 and number 2.
Okay.
So from there, the next lesson will be on, let me take there. What you take there? It will be on metallic bonding. Yeah, metallic bonding will be our next class. I don't want to continue that topic. I don't want to mix you unless you have any questions.
Awesome.
So if there is no question, we can end our lesson there. Remember to follow this. I'll be sending this link to the Google Classroom, the recorded lesson, so that if you want to review the lessons, you can review. I have recorded it, so I'm just going to send it in the Google Classroom account. If you want to refer to something, you can use that recorded video. So have a nice day. See you in the next class.
Thank you.